When we approach the heart, it's good to review and make use of our anatomical terms. I mean, I know you know where the heart is for putting your hand over your heart for the Pledge of Allegiance in grammar school for many years. But your heart it's anterior to your spine, right? It's anterior to your trachea, your esophagus. It's posterior to the sternum or breastbone that provides it with protection, right? It's superior to your diaphragm, and for those of which you are unsure, this is the big muscle that's parachute shaped and separates your thoracic and abdominal cavities. The heart is also medial to each lung. And as you can see, the heart takes up a little bit more space from the left lung than it does from the right. And this is the genesis of why the right lung has 3 lobes and the left lung has only 2. At its most inferior border, it comes to a point called the apex, and the apex is attached here to the diaphragm. The base of the heart is the superior border and is also attached to structures around it by collagenous fibers. The portion of the thoracic cavity that the heart occupies is called the mediastinum. This insert is a little portion of the heart wall of the left ventricle. So if we had to cut into someone's heart, the scalpel would pass through these layers from superficial to deep in this sequence. On the very outside, superficially, is this thick fibrous pericardium that secures the heart into the mediastinum and actually forms like the separating walls of the mediastinum. There's a parietal layer of the heart wall, and this is the parietal layer of the pericardium. And this is the same as any parietal layer or outside layer of any other serous membrane that we've seen before. It is superficial to a cavity, which is full of fluid. And here we call that cavity the pericardial cavity, right? And this pericardial cavity is full of fluid and trapped between the pericardial layer and the visceral pericardium, which has 2 names, which can also be called the epicardium. And that's because the layer deep to the epicardium is called the myocardium, which is made completely of contractile tissue that you can see here. This is all muscle. And then the endocardium, which is an epithelial lining of the chambers of the heart. And that epithelial lining has very flat, simple squamous cells, and we call that the endocardium. It's consistent or continuous with all of the lining of all of your blood vessels. And so collectively, we call all of that the endothelium. The pericardial cavity, it's like a fluid-filled balloon that the heart sits in. The classic example of serous membranes, like the pericardium and the pleural membranes that surround the lungs, the classic example is someone pushing their fist into a balloon, and the balloon kind of wraps around your fist with the air-filled wrapping between it. If this area becomes inflamed or filled with excess fluid, the fluid can prevent the heart from expanding during contraction, and this is what is called cardiac tamponade. Because the heart can't contract and forcibly eject blood, blood pressure drops. In response to all this, the heart is like, well, I can't pump more blood in each contraction, right? There's like not enough space for me to do that. So maybe if I pump faster, that'll work. And then heart rate increases, but it doesn't fix the problem. There's still excess fluid in the pericardial cavity that's pushing against the heart. On the outside of the heart, there are all these structures that are called coronary vessels or the coronary circuit. The heart does not get high on its own supply. Sorry, I couldn't help myself. What I mean is that the blood that is flowing through the heart does not feed the muscular myocardium of the heart. The myocardium, or the contractile layer of the heart, it's not dipping into what it's forcing through the heart. In fact, what's really strange is that the heart, it feeds off of itself as though it were a separate organ. What I mean is like blood comes out of your aorta and gets routed to your kidney, right? And blood comes out of your aorta and gets routed to your heart, much in the same way the kidney gets blood. So on the outside of the heart, there are these coronary vessels. And like I said, some people call it the coronary circuit. These vessels run through the myocardium, but they really are, a majority of them sit on the superficial face of the heart, and they are very, very tiny. They also have a lot of high pressure, so they can be subjected to blowouts, especially in arteries. Okay, so now when the heart contracts, all of these arteries for a moment constrict and blood stops flowing, right? So when the heart contracts, it cuts off its own blood supply. And then the heart relaxes and they all open it up again, filling with blood that feeds the contractile layer of the heart. I find it kind of interesting, right? That the heart, like as it contracts, it shuts off its own blood supply. The heart, though, it gets blood just like any other organ coming off the aorta. But this doesn't apply for drainage. Actually, the heart has this really big basin that you can see here, the blue, the coronary sinus, and it collects all the blood from the veins of the coronary circuit, and it dumps that blood back into the right atrium. This is a heart attack, which is more specifically or officially called a myocardial infarction. What it means is that there's a little blockage right here. And this myocardium, it's not being fed glucose and oxygen, and the muscle tissue starts to die. This is like if you or I sit like cross-legged on the floor and shut blood supply off to a foot, right? You're like, oh, my foot is asleep, and it starts to tingle, and you can't really contract it, right? Well, this is like when you do that to your heart. It's asleep. And this is what is called a myocardial infarction. If cardiomyocytes die, the cells that do the contraction, then, I mean, just like any skeletal muscle, they're going to start to release their actin and myosin into circulation as they break down. Remember, actin, it had tropomyosin and troponin that all helped make up that actin filament in skeletal muscle. Well, if you don't remember, now is your chance to stop this video and go back to the muscle chapter and review. All right, so to detect a heart attack, we might first take blood from you and look for cardiotroponins. After that, then we might do some imaging of the heart to try to find a blocked artery of the cardiac circuit. And we can declog or bypass the blocked artery. And these two pictures here, these are great pictures illustrating how a coronary artery can become clogged by years of bacon consumption. But it also, the picture in the top right is really great because it shows you how we can use your radial artery or your saphenous vein to make a bypass for your cardiac circuit. I find this helpful. The rule of four, right? That there are four chambers in the heart, there are four valves in the heart, and there are four vessels in the heart. So at the very least, you should be able to label this 2, 4, 6, 8, 10, 12. You should be able to try to label these 12 structures on the heart. Now, just as a warning, this picture that you see here is not a realistic picture. Realistically, I would not be able to see the pulmonary valve and the aortic valve in the same view. Let me use a green highlighter there. I shouldn't see this. The pulmonary valve should actually run anterior to the aortic valve, obscuring its view. But of course, I mean, that doesn't help us in this class. So just so you realize that these pictures that show both of these valves are teaching tools for us so that we can have one picture that shows all 12 of these structures.